Hi, this is Group 6 for the INET 4002 class, the fall 2025 semester with Professor Raby. Our presentation is on modern fiber networking infrastructure. The group was made up of Ling Tao, Amanda Lala, Bowen Keller, Tyler Zhang, Jacob Black, myself, and this was created today on November 14th. Next slide, Amanda. Yep, so this is just fiber networking. As an overview, as an introduction for us, we are going to cover how does fiber optic cables work, and that's going to go into single mode versus multi-mode, the two different cables and how they kind of differentiate between each other and how they work. We're going to cover the connectors such as LC, ST, KRJ, and other connectors that are used today in fiber networking. We're also going to cover the uses in the industry such as ISPs, data centers, and common work centers. We've covered fiber-centric devices like MIDI converters using copper and fiber in conjunction with each other. And we'll also compare fiber to other infrastructure mediums like unshielded and shielded twisted pair cables, serial and coaxial cable.
So next we'll talk about how fiber optic communication works. First off, the definition for it is how data transmitted as light goes through glass or plastic fibers. Next, we use the light sources, which is the use of lasers or LEDs. The mechanism towards it is the use of total internal reflection, which overall just keeps the lighting reflecting inside the core without it escaping. The efficiency for it is the use of high-speed data transmissions over long distances with a minimal loss. And unlike traditional copper cables, fiber uses light instead of electricity, making it faster and efficient. So one of the major topics we'll talk about is the single mode fibers, which is a it's just it allows one mode of light in a straight path with any minimal interference. Usually the core is very small for like 9 microns of diam diameter diameter, and the performance is the high bandwidth, low attenuation, and the long distance communication. So in the images, it shows how the single mode fiber signal is pretty much very thin, as you can see, just one straight path compared towards the multi-mode fiber. Usually they're all of them yellow, so that's how you can tell the difference between them both. And the multi-mode fiber, which is pretty much it allows multiple modes of lights to travel simultaneously. It is usually about 50 to 62.5 microns of diameter. The performance is just a short distance transmissions, has a lower bandwidth compared to the single mode, but it's easier to align during installation.
Okay. So for connector types, to start kind of at the earliest connector that we're going to talk about, it's the ferrule connector. It was developed by the Nippon Electric Company in the early 1980s. It has this little 2.5 millimeter ceramic ferrule, and this connector is known for it has like a screw-on fitting, so every time you install it, you have to screw it on, and then it's spring-loaded in there, so it has a really good fit, which is something that people favor it for. But it's a little bit less popular today just because further iterations of this design have come out and have kind of improved on it, for the most part. So then our next connector is the straight tip connector. So this is also uses that 2.5 millimeter ceramic ferrule. This one was made by AT&T about 5 years later. And this one you can kind of see in the picture. You slide it on and then twist it. And so then instead of having to screw it in, it's a lot easier to install, which made it pretty popular in enterprise networking. And it still is sort of popular today, but it's not as popular as some of the upcoming connectors. So then the next one is the subscriber connector. People also call this one the square connector, which is, also fits the SC acronym. But this one was created by the Nippon Telegraph and Telephone Company in the 1980s, like the mid 1980s, around the time when straight tip came out, and they kind of directly competed. Um, This one is more popular today, as I understand. It still has that same 2.5 millimeter ceramic ferrule. But this one you can just push on and pull off, which is pretty convenient, and it's really popular in telecommunications still today. And then next is the MTRJ, the Mechanical Transfer Register Jack. This one was made by AMP in the 1990s, excuse me. This one has it's one of the first to have the development of shrinking the ferrule down to 1.25 millimeters, although this one's plastic instead of ceramic. It is similar to the RJ45 connector design, which if you don't know, that's like the one that we use in our homes all the time. It's the Ethernet or the phone line connector. And this one gained some popularity at first because it had that smaller ferrule, but it's mostly used in legacy systems nowadays, and has kind of fallen out of favor for the following connector, which is the Lucent connector. Um, the Lucent connector, if you could go to yes, thank you. Yeah, there we go. So yeah, it was developed by Lucent Technologies in 1996. It has the smaller 1.25 millimeter ceramic ferrule. It's push on and pull off, and it's really growing in it's already popular and it's continuing to grow in popularity. It has really high performance with like installation and removal. It's got very low loss. Um, it's high density. It's able to be used in the field, so it's really popular. The only downside is that the cost per fiber is kind of high. And that one image you see over there, that's a duplex LC connector, so but you can get them in like the single connectors as well. But yeah, they're really popular, used all over the place for all different kinds of things. And then the last one we have is the MPO and MTP. So that's multi-fiber push on and multi-fiber termination push on. So the original MPO was designed by the Nippon Telecommunications and Telegraph Company in 1986, and then it was updated by US Connect in 1996. So what they did is they just took the original design and they just made it so it had tighter tolerances and higher performance. But they're still compatible with each other. It's backwards compatible. So instead of using a round ferrule, it uses a 6.4 millimeter by 2.5 millimeter composite ferrule. It's push on, pull off, and it's not very good in the field because it's not so good with like dirt and debris and potential things like that coming around. But it's really popular in centers because it has super high density because you can fit like usually 12 or 24, but I think you can fit up to like 64 fibers in there. And the cost per fiber is pretty low compared to other things. The cost per cable is high, but if you look at cost per fiber, it's pretty inexpensive. And it's pretty efficient, and it's favored for high amounts of like bandwidth. So yeah.
Okay, so fiber optics form the backbone of the global internet. Internet service providers, or ISP, use long-distance fiber cables to move massive amounts of data between cities and centers at high speeds. Fiber can also travel very far without losing signal, and so it's able to scale easily as demand grows or lessens. This makes it one of the most reliable and fastest way to deliver internet around the world. At the local level, fiber is used for things like fiber to the home, FTTH, and fiber to the building, FTTB. These connections give neighborhoods and apartments much faster speeds than compared to old old copper systems. Many cities are also building fiber rings for redundancy and outage prevention. And so, yeah, this helps neighborhoods stay connected to the nearest local network hubs. Fiber optics are also important in places like data centers, manufacturing, and schools and universities. In data centers, fiber links servers, switches, and storage for cloud providers like AWS and Google Cloud. In industrial environments, fiber is safer because it isn't affected by electromagnetic interference. So it's really ideal for such an environment. And then schools and universities use fiber for online learning, research, and high bandwidth applications across campus. And so fiber isn't just used in big networks as well. It can also be used for individual workstation. Fiber to the desktop, FTTD, gives a direct fiber link from the switch to a user's computer. This kind of gives the workstation a higher speed, more bandwidth, and less signal loss compared to copper, kind of bringing that enterprise level performance straight to a single user. So media converters are small devices that let fiber networks connect to standard copper Ethernet equipment. They work by converting light signals from fibers to electrical signals for copper. Could also go either way as well. They come in many different speeds, and some models even support power over Ethernet for devices like IP cameras or APs. Since media converters needs its own power source, having too many in one area can cause power saturation, and so planning is pretty important. And then here are just the pictures and kind of how the process of media converters are used. And then we have small form factor pluggables, FFPs, SFPs. They're small removable modules which are used in switches, routers, and servers to support fiber and copper connections. They come in speeds like 1G, 10G, 25G, and even 100G, which is QSFP, uh, quad small form factor pluggables, which the difference is a single SFP uses a single channel, and quad SFP uses four channels. Unlike regular copper ports, though, that auto-negotiate speed, SFPs must match on both ends, meaning that the speeds must match each other. This just gives network the flexibility to kind of mix for fiber types and distances without like replacing the whole switch. And so here we have pictures of the different SFPs.
Fiber optic cables compared to other mediums. First one is UTP or unshielded twisted pair cables. One of the most distinct things about these cables are their design. They use copper wires that are twisted together. But one of the distinct things is that they do not have any metal shielding surrounding the wires, which makes them very susceptible to electromagnetic interference. But because of this, they are generally more flexible and cheaper to install, which is why they are pretty common. They're still pretty common in today's networking cables. Some of the more common ones are Cat5e, Cat6, and Cat6a. STP wires or shielded twisted pair wires designs are similar to UTPs, except that the twisted copper wires have a foil shield or embroidered metal wiring around these wires. This helps block out electromagnetic interference, which is very useful in very electric heavy environments. But because of this design, they are generally thicker and less flexible. Um, and but when it compares to copper wires, the electromagnetic interference is a lot less, which makes it a better option. Next is coaxial. The design is a bit different compared to STP and UTP. The coaxial has a central conductor or a single copper conductor in the center, surrounded by an insulating layer and then a metallic shield. Because of this heavy shielding, it can carry higher frequency signals more reliably than the other two cables. Some connectors include BNC, F-type, and N-type. Although they are very heavily shielded, they are still a lot slower than fiber, which makes fiber cables support far greater speeds, which is why fiber cables are often a better option than coaxial cables. And lastly is serial. There are a few different types of serials. RS32 is one of the most common ones. It can be used for old computers and peripherals such as printers. RS-422 and RS-485 are also pretty common cables that, although these cables are very old and not as fast as fiber, we can still find them in homes and offices for things like routers. And although and they don't go or they are not as fast as fiber and they don't travel as far as fiber optic cables.
All right, and to conclude, go to the next slide. What we have covered is how fiber works, the differences between the two cable types, single mode and multi-mode, the different connector types that we have available, different uses of fiber in industry, devices make fiber communications like there's SMPs and other networking mediums that are similar and or comparatively to fiber. That was our presentation. Thank you for watching this.